Good evening.
Now let's get on to the business. So we have understood now angular momentum. Angular momentum of a particle. Angular momentum of a particle belonging to a rigid body. Then we have seen the angular momentum about the centroidal axis. Angular momentum of the body about a axis not passing through center, and we have also analyzed the angular momentum of a rigid body for with respect to a reference point which is outside the body, considering both the translatory motion as well as the rotational motion. Okay. Now we shall go one step ahead. Okay. So the analysis for this is exactly same. Okay. What I am going to do now is same. Only thing is, yesterday we used to have, say, a body of mass m moving with velocity v bar. So this was mv bar vector. Okay. Mv bar vector, and then we referenced it from here with say O, and if I say this point is P, so this vector was RPO bar. Okay, so this is what we did, and we got the momentum at this point LO bar given by RPO bar cross MV bar. I suppose all of you we have gone through this type of things, right?
Yes.
So we did a lot of analysis. Now what we will do is we will replace this vector. We will replace that vector by another vector. Okay, so this is still RPO bar with respect to O, and this point P I will replace it by a force vector. Okay, so here it was this. Now here I will create a new vector here called as tau bar. Tau bar of O will be equal to RPO bar cross M. Got it? Hello?
Yes, sir.
Yes.
That's all we are going to do. We are just replaced it. So this one, angular momentum, was a concept we understood yesterday, and torque is another concept that we are going to understand today. Okay, and we define this concept by this mathematical expression, and we are defining this torque by this. Okay, well, it has its own significance, it has its own physical significance. I will go into the details of that. So all that analysis I did with different diagrams for this. I repeat, what all analysis I did for this angular momentum L bar with different diagrams, if you recollect, the same analysis I will be doing it, but only replacing mv bar by f bar. Okay, that's all. So then you will get all the expressions that we got. Wherever you had L bar, it will be replaced by tau bar. Got it? That's all. Basically, that's the difference. Okay. Here we go. Okay. So before I go to the next point, I would like to mention here that this is an important abstraction which I had forgotten to tell yesterday. LC is called spin or internal or intrinsic angular momentum. Now, what it means is, now you know an electron is spinning as well as it is rotating about a fixed axis, or we say an electron is revolving. So it is spinning about its own center of mass. Electron is spinning about its own center of mass, and here you see the spin is around its center of mass. It is not with respect to any reference point. Okay, and such a type of a body on its own spinning, okay, it is spinning about its center of mass, and we call that as what? Internal spin or intrinsic spin. It is independent of the coordinate system. It is an intrinsic property of rotating body. So you see, electrons intrinsic property. Intrinsic means the day electron was born, then it was spinning and rotating, same like Earth. Okay, so that is called intrinsic. Puttu guna. However, angular momentum of the center of mass of rigid body depends upon the frame of reference. Obviously, if this electron is spinning, then its angular momentum is fixed. But if this electron is also in motion with respect to reference point, its angular momentum will also change. Okay, now let's get into torque, right? Torque, moment of force, that is, you know the difference. When it is static, we say moment of force, otherwise we use the word torque. Then, torque of a force on a particle about a chosen reference point. Extremely important, the torque of a force on a particle about a chosen reference point is the ability of the force on the particle to induce angular acceleration on the particle, right? So torque is the ability to induce angular acceleration. Okay, right. Defined on a particle, and it is defined as tau suffix O bar is equal to R suffix P slash O bar cross F. Okay, as I already defined. So mathematically it is defined like this. Okay, right. Now going further, we already know something like this, right? We know that L bar of P with respect to O is R of P with respect to O cross M V bar P. This is already known to us.
Yes.
Now we'll relate now tau with L. We'll relate tau bar with L bar. How do we relate? If you differentiate this, that is d by dt of L bar, then go on differentiating the two terms. So we get here dr bar by to bar equal to v bar p with respect to o cross mv bar plus r p with respect to o m d by dt of v bar gives you the acceleration p with respect to o. Now we can interpret this like this. Okay. So you can see here the first term. We'll discuss this, why it becomes 0 here. We'll discuss this. Okay. So here we are going to end up with see here the idea here is here tau bar contained what? F bar. Tau bar contained F bar. Hello.
Yes.
Now you can see here V bar PO, M is a scalar quantity, it can be pulled out. A bar cross A bar, if you take, then its cross product is 0 because the angle made by the two vectors are 0 or 180, they are collinear. So this term goes off, and by Newton's second law, you know M A bar is nothing but the force or the net force. So therefore, we get the term tau bar. You can see, you can compare this. You can compare tau bar here contains RPO and F. Here, d by dt of L will contain the same two terms. Okay, so therefore, the left hand side dl bar by dt is nothing but tau bar. So this is how tau bar gets related with L bar, and that's what it is. Okay?
Yes, sir.
And this cross this is called F net. F net why? Because now here there can be many forces acting on the body. So you have to take the vectorial addition of all those forces. That is why the term F net bar is used here.
F net bar. Yes.
Okay, that's it. Now the direction of that torque can be plus or minus k cap. That is now tau bar is d by dt of L bar. L bar is what? I naught into omega bar. Okay, I naught into omega bar. Now, so if you pull the I naught is a constant. So here I naught cross d by dt of omega bar. And d by dt of omega bar will give you alpha.
Yes.
But remember this thing here, okay? So you have to understand that what is this cross here? This is simply a multiplication, not a cross product.
Yes. Yes.
So you get a tau bar is equal to I naught alpha, and we got F is equal to M into E. So this is it. Okay, quite simple to understand.
Yes, sir.
Now here is something which is important for us. Again, you see here, this is the reference point, and if you take, this is the rod, and at this point of the rod, if force F is acting, then we know that we will split this into two components, F sin theta, F cos theta, and again you can see with respect to a particle also, you have a similar diagram, and therefore now here you see the twisting that happens because of the torque. That is, whenever the force is not passing through the center of mass. That's what I said. Okay, the twisting is because of the component F sin theta. So, frankly speaking, the torque effect. That means torque means the effect of the force to rotate the body, or a tendency to rotate the body, is proportional to RF sin theta. To be very frank, it is proportional to RF sin theta. Okay. So, magnitude of the torque of force is proportional to the product of the distance and the point. Please remember that in Newton's law also, we got F bar is equal to K M A bar. So, Newton's law said the force is proportional to the rate of change of momentum, linear momentum. So, the constant of proportionality we got was K. So, we wrote F bar is equal to KMA.
Yes.
So, in SI system, we chose M to be 1 unit, A also to be 1 unit, and then we also said the corresponding force due to this is also 1 unit, and therefore K reduced to 1.
Yes.
Right? In the same way here also, we will get these quantities, that is R is unity, F sin theta is unity, and then we'll designate tau also as unity, and then the constant of proportionality will also become 1. Okay, and it is a dimensionless quantity, and therefore torque, we finally write torque as tau bar is equal to R bar cross F bar. Same like how we did it for the force. We defined Newton, if you remember, right? And OQ is called as the momentum. Clear, friends?
Yes, sir. Yes.
Momentum.
Yes.
Perpendicular distance. So here this vector, you draw the a line through the line of action of force, and drop a perpendicular from the reference, and then this force into this perpendicular distance. That is the torque.
Yes, sir.
Okay, geometrically. Now torque about a point and torque about an axis. Okay. So here you see we have defined torque of a force about a point and the force dealing with it. When the body is in plane motion, the net torque of all the forces, including the forces necessary to restrain the rotation of axis, is known as torque about the axis. That is, you have a body, which can rotate about this axis. Then whatever forces are acting, 1, 2, 3, 4 forces are acting on this. Okay, so all those forces are creating individual torques. So the total torque is the net torque becomes, okay, the net torque you have to take it along the axis of rotation. So torque about an axis of rotation equals the moment of force about the point where the plane of motion of the application intersects. Okay, right, that's it. Okay, fine. So let's break the monotony with this. Imagine a car moving with uniform velocity on a level road observed from a point O on the footpath. I hope all of you can imagine this. What is the torque on the car C about O? Is the vector OC rotating about O? Is omega bar constant? Please, Aram se write the answer in your notebook. What is the torque? Is the vector OC rotating? So I suppose you draw some diagram there. Diman?
Sir,
No diagram.
I do diagram.
Then from that we abstract. So if your diagram is clear, so you can mark this car and say the car is in motion, V bar. You can assume the mass of the car to be m, and this is the footpath. So you are referencing it with respect to. Now they are asking you what is the torque acting on the car.
Yes.
Okay, so what is the keyword here? It is moving with uniform velocity
On a level.
on a level road. That means no force is acting.
So, torque is.
So therefore torque is zero.
Yes, sir. And but
0. Yes, sir.
Tau bar naught is equal to zero because no external force is acting. But as I said yesterday, this point is moving. So therefore this r bar vector, this theta is changing
Rotating.
rapidly, and the most important thing is it is rotating, no doubt. No doubt this is rotating, but you see this perpendicular distance from this is not changing.
yes, sir.
Yes, sir. Yes, sir.
Angular momentum
So angular momentum is constant.
is
Constant.
Yes.
So angular momentum is constant. But angular momentum is constant. But what about omega r?
Sir, it's not constant.
Omega r is not constant. See, L bar is constant. L bar is constant. Okay. But what about omega bar? They have asked that question. Is omega bar constant? Okay. So why? Because L is equal to m omega r.
R.
Yes.
Sir, R.
Isn't
Sir,
it?
MBR.
Sorry. MVR. MVR. So V is equal to omega r if you express. Then you will write it as m
Omega square.
MR square into
mr square into
Omega.
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 So here you see this r is increasing. Therefore omega should decrease.
Yes, sir.
Yes, sir.
So therefore omega is not constant.
Sir,
L bar is L is constant, right?
Yes.
But omega bar is not constant. Omega bar is changing.
Yes.
And the torque is zero.
Torque is zero.
Yes, sir.
Clear?
Yes.
So it is better that you write the diagram and the expressions, and you should be able to hunt out the things.
Yes, sir.
Okay?
Is the vector.
Yes, sir.
Okay, fine. So this is constant. Omega bar is non-constant. So it's correct. Attempt this problem. Electron of mass m is moving with uniform speed v in a circle of radius r about a proton of an hydrogen atom. What is the angular momentum and torque of the electron about the center of circle? This is something you should tell. The angular momentum of the electron. Just now I wrote.
Yes.
Right? Yes, tell. Somebody tell.
MR square.
MBR into minus k cap.
Because they give you V.
Minus
Yes.
k cap, sir.
Yes. MVR into minus K cap. Agreed? Everyone?
Yes, sir.
Sir, they have not given whether it's going in clockwise or anti-clockwise.
So why did you say? They got.
Yes.
So it is plus or minus K cap.
That's what.
Yes, sir. Minus k cap.
Then what about the torque?
Zero, sir.
Torque is
Zero.
0. Why
Zero.
torque? Why torque is 0?
Centripetal force acts, sir, but the cross product will be zero. sir.
Yes, only centripetal force is acting. There is no tangential force.
So-
So therefore, the torque is 0.
Zero.
Please, all of you very confidently but cautiously, you start answering.
Okay.
That is what I say. Confidence should be there, but caution must be there. You should not just, start throwing things out, because now you will be what? You will not simply be told, hey, it's not correct, but in examination, you are going to lose marks, negative marks for that. Okay, and this competition is very, very thick. Correct? Yeah. Alright, good. So there's only centripetal force, so it's right. This one. Consider a bob of conical pendulum. So I given you what is meaning of conical. This is not there in the examination. They have only asked, consider a bob of conical pendulum. What is the angular momentum of the bob about the point of suspension? They give. So this is the problem given in examination. I am sure many students would have asked me what is conical pendulum. So therefore I have written this. Okay. See, that day I showed one thread is there. You have tied a bob. So this bob, if you do like this is called simple pendulum. Now you hold the bob like this at an angle, and then you make it to rotate.
Conical.
Okay, that becomes a conical pendulum.
Yes, yes.
Got it? That's it. So this is a conical pendulum. Now what is the angular momentum of the bob about the point of suspension? Okay? Yes, please do it.
Yes, sir.
Uniform speed V.
Find angular momentum only or torque also?
Yes, sir. Only angular.
We don't know. They ask you what is the angular momentum about the point of suspension.
Yes, sir.
They asked what is the angular momentum about the point of suspension. So the V bar vector is like this, and this line itself, this length of this one will be itself becomes L bar from O to the point P, P1 and P2 points.
Yes, sir.
So the angular momentum will be this and this line. So this will be what?
And
L bar cross M V bar,
V by yes, sir.
Yes,
isn't
sir.
it? So that becomes what?
Yes,
The
sir.
angular momentum.
Yes, sir.
Okay. So angular momentum over to O bar will be M, right? Sorry, this will be equal to L bar. In this case, L bar is from O to point P cross M V bar. This will be the angular momentum. Hello.
Yes, sir.
Yes, sir. Yes.
Yes, sir.
ठीक है? So it is a constant. ठीक है? और because speed is constant, L is constant, M is constant, so angular momentum is constant. ठीक है?
Yes, yes.
Yes, sir.
So the question
Sir,
is, wait a minute here. So L bar, L naught bar is equal to so and so. So L naught is equal to MVL sin theta. This is constant. But now the question is, I am asking another question here. Is LO bar constant?
No, sir.
Sir, what?
See, look at this question now. So what we got is the magnitude of the angular momentum is constant. But is the vector angular momentum constant?
Sir, one doubt, sir.
Huh.
There is mg sin theta acting along that motion of that bob, sir. So then there is an external force in it.
सब जोर मात्रा रखे.
Like there is a force like mg sin theta which is acting along the direct motion of that bob, sir.
Wait a minute. MG sin theta. What is it doing there?
Like the component, sir.
What component along what?
Like in which direction it's moving, no, sir, even it's also moving in that direction.
MG is moving in that direction.
Not mg, sir. The component of mg, sir.
component of mg is moving in that direction. Mg is always down.
So that not like when we consider sir, like this tension force is balanced by one component of mg.
So see, everywhere as the conical pendulum is moving like this, mg is everywhere there.
Mg is everywhere.
Mg is also say the same and tension is also same. But the direction of mg is not changing.
Direction of mg.
But the direction of tension is changing.
Yes, sir.
The direction of tension is changing.
Yes, sir.
Okay, right? That is changing.
Yes, sir.
So therefore now we get an expression L naught bar is equal to L bar cross mv bar. This is standard expression. Now if we evaluate for only the magnitude, we get mvl sin theta. See, as far as the angular momentum is concerned, mg is not playing a role.
Yes, sir.
Because they have given us velocity and mass.
Yes.
So the magnitude of the angular momentum is constant. Look at this expression.
Yes, sir.
Now my next question, you got this?
That I got.
Now the next question is L naught bar, is it constant?
No, sir.
Why?
So the direction of L naught bar is changing.
Yes, direction of L naught bar is continuously changing. Because you see, when the bob is here, the R bar vector is like this and mv bar vector is like this. So if you take the screwdriver and turn it like this, the L bar vector will be what? It will be perpendicular to the plane containing what? The V bar vector and the R bar vector. That is understood?
Yes, sir.
See, now if you say the bob, I am just holding this plank here at an instant when the bob is here. Can you see my finger here?
Yes, sir.
Bob is here and it is going into the board. So I am holding this plank. So if I hold this plank, then the line from here to here becomes L bar.
Yes, sir.
And a line perpendicular to this becomes mv bar.
Yes, sir.
So L bar cross mv bar. The screwdriver will turn into the board. So I will get a vector which is going into the board.
Yes, sir.
And this is the direction of what? The L naught bar.
Yes.
At this position.
Yes, sir.
And this L naught bar will travel perpendicular to this plane.
Yes, sir.
But it is always changing.
Yes, changing in direction.
I hope all of you got it.
Yes. Yes, sir.
Yes, sir.
Yes.
So that is it. So therefore the L naught vector is not constant. Right? Hello?
Sir,
Yes, sir.
My next question is, see, that means now from the theory that we have learned here, the L naught vector is changing means what? D by dt of L naught bar is not constant. That means now there must be torque acting on the system.
yes, sir.
There must be torque acting on the system. Okay. Now, how is the torque coming to the system? And why is the torque coming? Why the torque is present?
So there's an unbalanced vertical component of gravity is perpendicular to the strings.
Yes, sir.
There is an unbalanced
Component of gravity which is perpendicular to strings.
external. Excellent. Okay. Instead of that, yes. So if you take one component of gravity in direction with the tension,
Yes, sir.
it gets balanced. That's what you said.
Yes.
Okay. Fine. And there is another unbalanced component, as we used to see in the case of pendulum. We used to call it as mg sin theta. So that mg sin theta, that is now if you take this here, so if you take this as theta, so this becomes mg cos theta and this becomes mg sin theta. Okay. Now this vector mg sin theta is unbalanced. So this unbalanced vector mg sin theta, and again you see the same this vector L bar cross mg sin theta.
Yes, sir.
So you will get a vector, the torque vector which will be again out of the board.
Yes, sir.
Hello.
Yes.
This torque vector will be out of the board. Okay.
Sir,
Yes, please.
To the board.
L bar is like this, and mg is like this. So L bar cross mg, L bar cross L bar is like this, mg bar
mg
sin theta. I am taking it. See, this is the tension. So mg cos theta is like this, mg sin theta is like this.
Yes, sir.
Mg is like this.
It's into the
Okay, MC, this is the one. Mg is down. So Mg cos theta is here. Mg sin theta is here.
Yes, sir.
Mg sin theta.
Into
So
the-
L cross Mg sin theta
into
will be into the board. Okay.
Yes, sir.
Will be into the board. So it is into the board. And what is the direction of our L bar vector here? For our L bar vector, it was what?
From more
L bar into mv
yes, sir.
was like this. So again, L bar into mv, the torque vector was outside the board,
Outside
isn't it? The torque vector was outside the board.
yes, sir.
And this is definitely not aligned with it. And therefore, this torque vector is responsible for, d by dt of L naught.
Sir, this torque is acting perpendicular, sir. So it should stay in the magnitude of
Yes, and therefore this is perfectly correct. I was coming to the point. So this tau bar naught is acting perpendicular to L naught bar, and therefore only the direction of L naught bar is changing, but not magnitude of L naught bar. Just like how the centripetal force will only change the direction of motion, but not the magnitude of motion.
Yes, sir.
Yes, yes.
You are getting grip? Fantastic.
Yes.
See now, the entire motion, complex motion, you are able to comprehend. Fantastic. Okay, and this is where the struggle is all about, vectors, how you are going to see, this is like this is like this happens like this. And in the heat of the examination, you should be able to comprehend it and write it correctly.
Yes, sir.
And you will be able to do that. Okay, your brain power will be increasing tremendously. Okay, and be brave, be confident, but be cautious.
Yes, sir.
Right? And learning is going to be fun. All right.